reason why, because isentropic means that you could actually extract the max work out of the turbine versus you have losses and you didn't extract the max work out of the turbine. So from that work turbine, so this is a critical one and everybody keeps forgetting this. The work out of the turbine is equal to the work out of the compressor. If I have one single shaft and I'm not using that work for anything. So propulsion systems, most likely your shaft work is equal to whatever you're propelling because we don't have a generator here. So it's equal to work out of the compressor. And that's equal to 1 plus FB, the fuel to air ratio, multiplied by CP, TO4 minus TO5, which is your heat addition through combustion. And your pressure ratios PO5 to PO4 is equal to your isentropic temperature relative to your max temperature, and it's gamma over gamma minus 1. So from these equations, I get TO5, TO5S, work of the turbine output if you need it, and PO6. And that's pretty much it. Now, we need the afterburner. And obviously, nozzle. But it's the same stuff that we've done on ramjets. All the difference was the compressor and turbine. So for afterburner, how do I deal with the secondary burner? Well, I have a secondary burner right here. I have flow that's coming at it. That flow is 1 plus the fuel-air ratio from the main burner multiplied by M dot A, so it's a conservation of mass. Then I'm adding some M dot A multiplied by a FAB, which is the afterburner. So what that's going to give me is 1 plus FB plus FAB. That's about it. Very, very simple. So from that, FAB is equal to M dot FAB divided by M dot A, and FB is equal to M dot FB over M dot A. So, assuming that you have complete combustion, which means the efficiency is 100%, meaning what Jason is doing is, I'm not considering it here. So I'm assuming efficiency of 100%. So assume, well, it's not the real situation, but I want to deduce the equation so you see them cleanly without the efficiency. Assume complete combustion. What do I have? I have 1 plus FB plus FAB M dot A multiplied by H6 of my afterburner minus 1 plus FB M dot A, which is the enthalpy that is coming in to my afterburner, which is PO5, is equal to the fuel to air ratio of my afterburner multiplied by the mass flow rate of the air that's passing through multiplied by the heat of combustion of the fuel. So from that, this cancels out, this is canceled out, this is canceled out, rearrange the terms, and what we get is FAB is equal to 1 plus FB TO6 actual, or you could just write it TO6 of the afterburner, TO5 divided by heat of combustion, CP minus TO6 or afterburner. And when you notice, this equation looks very, very similar to the combustor equation that we've done before. The difference is I don't have my efficiency, so if you want to add the efficiency right here, you could say efficiency of the afterburner is multiplied by the heat of combustion. So we have to treat the afterburner the same principle that we did with combustor. We have to assume, again, say FAB plus FB has to be less than stoic or equal to stoic. If it's not, then we have to get the max temperature again. And PO6 of the afterburner is equal to the pressure ratio across, or the pressure drop across the afterburner, PO5, the ignition pressure that was coming in. And from that, you could actually get PO6A. And finally, the nozzle. Assuming adiabatic, so TO7 is equal to TO6 of the afterburner. Will give us QO7. The pressure ratio is relative to ambient, so PO6 relative to my ambient condition 7 is equal to the temperature ratio of 6 relative to temperature ratio, since it's adiabatic, relative to 7S, and this is gamma over gamma minus 1, and from those two I could get P7, T7 if they're not on isentropic, if they're not on the same level, if it's not ideally expanded, which this is a real engine, so it could potentially not be ideally expanded. Thermal efficiency again is equal to what we did for the turbine.
We did.
PO6. Oh, sorry. TO6, which is hotter temperature relative to T7 over TO6 minus T7 isentropic. From that, I can get T7 isentropic. And knowing that, I can get actually my velocity T7 is equal to my Mach number of 7 multiplied by gamma on T7.
This is doable.
And actually, if I know this, I could use this to get TO7 divided by 7, which is going to be a function of your gamma and Mach number. Mach number at 7 and gamma. And from that I could get M7. And substitute it in there and get my velocity at 7. So this is sort of the formulation for a real engine. Let's do a quick example to tie all this in. So we're going to be writing the same equations again. So that's propulsion systems for you. It's lengthy and it's a